Hi, I'm Sala, and in this video we'll discuss some options for delay approximation in continuous time. Delay in physical systems is usually a result of a transport phenomenon in which some mass, energy, or information goes from one place to another at a finite speed. So, to exactly model this pipe moving hot water, we need to store all the temperatures at each longitudinal position in the pipe. But there are an infinite number of positions, so we cannot exactly simulate it with a computer with finite memory. Of course, we can store every millimeter of it, let's say. Okay, that's spatial discretization. More on that later. Or in general, if we have a time delay, we can pursue a discrete time approximation in which a delay of 1 second is simulated by storing a signal every millisecond, 1000 samples, and interpolating between them. That would be a time discretization. However, in this video we will not discuss time discretization. For, let's say, control design methodologies, or for approximating this as part of a larger system, the issue is that we pursue having some continuous time GFS of hopefully reduced order, let's say order 3, 4, 10, to approximate this pipe instead of storing 1000 samples or positions and handling them with specialized code. Okay, so this is our goal, continuous time delay approximation. In this case, this is the transport partial differential equation. We can solve it by several methods, for instance, carrying out Laplace transform in time domain, and then, if we wish, a transfer function, we can move up things and set initial conditions to 0. And now, considering S to be an algebraic variable, we end up with this ordinary differential equation on the position x. This is a first order ODE, which has an exponential in x, with the coefficient of the exponential being s over v. Here we have it. And this exponential multiplies the initial condition, which is actually the Laplace transform of the inlet temperature in this pipe. So that would be the input to my transport delay pipe, u of t, and u of s will be the Laplace transform. So this will be the transfer function of the transport delay for constant speed. This exponential in s is the delay Laplace transform that is usually taught in undergraduate courses when Laplace transform and transfer functions are introduced. So the issue is that we wish to approximate this exponential, and we wish to compare several of the simulations. So we will give a value of 1 to test 1 second delay, and these lines are one way to insert exact delays to the control system toolbox in MATLAB, so that MATLAB does whatever internal symbolic or numeric manipulations it wishes. But now we wish some approximations, because this partial differential equation is of infinite order, so it cannot be simulated. So we'll propose, for instance, the so-called Padé approximation. The Padé approximation is based on approximating a pair of functions by equating the Taylor series terms, and in particular we'll compute the Taylor series of the exponential of ds, which is the delay, this one, and we will compute the Taylor series of the quotient of polynomials at the right hand side of this expression, something like this. And then we'll solve for the a and b coefficients. As we have n unknowns in the denominator and n plus 1 in the numerator, the degree needed in order to have an equal number of unknowns and that of equations is the polynomial of degree 2n, the Taylor series, with 2n plus 1 terms. So with n equal to this fourth degree polynomial approximating the exponential and the Taylor series of this fraction, computing the derivatives first, second, third, and fourth at s equals 0, then it will give me p, q, r, t, and w as functions of the a and b unknowns, and then I will be able to solve. Let us do this n equal to with a symbolic toolbox in detail, but of course the Pade command does everything transparently to us. So the quotient of polynomials in here will be encoded there, and then I will compute the Taylor series with 5 terms and get the coefficients of that thing as a polynomial in the s variable. So I get these coefficients for each of the powers of s, and then if I equate these 5 coefficients to those of the Taylor series of the delay, I called delta in symbolic toolbox such delay, then telling the solve command to find the unknowns that make the coefficients equal, then it outputs the solved values and I get this solution, which of course I could have obtained it as well with just one line with a Pade command. If a true delay is a transfer function from the control system toolbox, then it gets me this, but if I divide numerator and denominator by 12, I get this approximation for a true delay of 1 time unit, 1 second, and of course if delta is 1, I get the same as the symbolic toolbox manipulations. So well, with this equating of the Taylor series at the left and at the right, this is how Pade approximations are built, and well, I can tell MATLAB to give me, say, the 4th order Pade approximant, which is, this transfer function, or, 5th, 29, or whatever order I wish. We may even go up to, higher order, say 25. So it's a monster. And in fact, there are sort of numerical precision issues. You see that coefficients start growing and growing. So if we increase too much the order, then accumulation of round-off errors spoil the accuracy of all that, at least with the control system toolbox. But okay, it works with 25, and this is the so-called Pade approximation. As another option, it will be the finite element approximation. What does it mean? It means that I can split the pipe in two and say that I can approximate the delay of 1 second by cascading 2 half-a-second delays, or 4 delays of 1/4 of a second, or, well, I can split it into capital N elements and approximate the smaller delay of each of the elements with, for instance, the Pade approximation. This is the first order Pade approximation. It's the most commonly used order, and we raise to the nth power, 1 for each element. Well, this will be another approximation. Here's the MATLAB code. We divide the delay by n, do the first order Pade, and then raise to the nth power to get me a finite element approximation of the delay. In fact, there are other videos in which we detail the finite element approximation of this heating pipe, because, okay, when Q heating power is 0, we just have a transport delay, assuming the pipe is perfectly insulated. But if the pipe is not perfectly insulated and we put some heat on, then partial differential equations and their approximations need to be handled in a different way. See those videos for details. In here we just concentrate on a transport delay phenomena, insulated pipe, no heating. As a last option, we will try this only pole approximation, because, as we will see in simulation, these non-minimum phase zeros make some kind of inverse response and oscillations that we would not have in this case. So we will compare the high order Pade, the finite element with poles and zeros, and the finite element with only poles approximations. In fact, the two finite element approximations are extreme cases of this expression here that, okay, you just don't worry, you may skip this, or well, post video and analyze that beta equal 0.5 results in this approximation and beta equal 1 results in this one. That beta is used in the heater simulations, but okay, we'll forget about it here for brevity. So we will now discuss actual simulation results. We did set n equal 25, and in here we do step responses. You can watch all the code here if you pause the video, but the important thing is the result, the plot here. In blue we have the exact time delay response. Well, it would be exact if MATLAB did make a sudden step, but as plot puts a finite amount of points, then we get this almost exact blue stuff that it's almost vertical. The Pade approximation is the red one, sort of the best one. Finite elements, order 25 is the yellow one, and purple is the only poles. So now, if we concentrate on the first step plot, we see that Pade and the finite element first order Pade approximation have some artifacts going up and down due to no minimum phase zeros. But on the other hand, the slope here is faster than the all poles purple line, in which it starts perfectly horizontal, perfectly smooth, but it starts going up quite a long time before the actual exact delay at 1. So we trade off slope in the sudden increase versus oscillatory artifacts in the transient. Well, this is the step response. This may seem important, but actually it's not that important if this pipe is a subsystem of something much greater in which signals are smooth and have finite bandwidth. We'll see later on. For instance, if the input to the delay is a ramp, then all approximations, as we see in the center plot, have a very reasonable time response, and the oscillatory artifacts are much less noticeable. A satisfactory response is also, if the input or output temperature is going to be low pass filtered by a first order filter with sufficiently slow time constant, in this case 0.8. That's the bottom plot in here. So this is the 25th order time domain simulation, and if we go back and reduce the order, because this kind of approximations are usually meant for low order approximations, in fact in many applications we just stay with n equal 1 first order system and period, but okay, in here we have MATLAB, so we try quite a few things. So if we get a 5th order approximation, we've got here like 5 artifacts, up, down, up, down, up. We have not so steep slope, but okay, this 5th order approximation, Pade stop for instance, approximating a ramp or first order filtered input are quite reasonable, and in actual applications there are so many sources of modeling error that I might be perfectly happy with the red and yellow lines as an approximation of the blue ones, and even the purple one, depends on the smoothness of the signal. Purple one formally is not so good an approximation, but intuitively it kind of makes people be less suspicious about what the hell are we doing with this kind of oscillatory behavior. Everybody thinks that a delay does not oscillate. So depending on the audience, we can choose either poles, either, Pade stuffs, or we can tune these beta coefficients to our liking in order to convince our customers that we are giving them a sensible approximation of their transport phenomena. Let us now see how these things approximate in frequency domain. We have a 5th order approximation, and again, if I zoom out so you can have a look at the code, it's just both mag, cosmetic plots and labels and whatever. So let us concentrate on the meaning of this diagram. And in fact, it's important. True delay has both amplitude equal to 1, a sinusoid of amplitude 1 at whatever frequency it has. After the delay will indeed have unit amplitude, so it's kind of 0 dBs frequency response at all frequencies. And then we compare that unit gain with the modeling error in considering the several approximations of the delay minus the true delay. That's the modeling error in frequency if I do both mag. 1% error is minus 40 dBs, this green line. 10% error is this red dashed line, minus 20 dBs. So as we can see, first approximates up to, let's say, 0.3 radian seconds with less than 1% error. This finite element approximates to 1.5 radians per second, and this Pade order 5 approximates to 6 radians per second. What does that mean? Well, in robust Nyquist whatever control it means something, but for the moment being we can understand in lay terms these bandwidth numbers as sort of half period. Say for instance the half period of this 6 is pi over 6, so it's half a second. So it means that if signals go from some place to another one in half a second or less frequency, more time, longer half period, then our red Pade approximation will be 99% accurate. So if I am putting the hot water in this pipe in a tank that takes 2 hours to heat, then we are perfectly accurate with the red approximation and also with the purple one, because 0.3 radians, the half period associated to this frequency is sort of 10 seconds. So for anything that takes longer than 10 seconds settling time or something like that, the all pole approximation will be good enough, 99% good enough. And as we go on considering the half period, pi over these frequencies, that would be the sort of cycling time or speed of change, let's say, of the underlying signals if this pipe is part of a bigger system, in which we will guarantee 99% accuracy. Of course, if we increase the order of approximation and we go to 30, well, this is the step ramp and the first order, responses. And in frequency, increasing the order, we do increase the bandwidth up to which the approximation is good enough. For instance, this is like 50 radian second, 6 cents of a second of half period, so that order 5 got us 99% accuracy for applications with half a second settling time. And in here we get 6 times more complexity, order 30, but we get 99% accuracy in sort of 8 times faster applications. So choosing the correct order in a simulation for a given subsystem depends on what is connected to and the available computing resources so that we have reasonable simulation times. It's nonsense asking for a supercomputer to simulate 10 seconds of this pipe and taking 2 months to carry out such a simulation. As I said, in most of the applications, delay approximations stop in first or second order approximations. I put 2 and compute again if the bandwidth of the applications of the overall system is small enough. Most books will tell you to approximate the delay with a first order Pade and stop worrying about this. Okay, but if you are a master level student, you might wish to understand the issues we discussed in this video for a deeper comprehension of what an approximation means. So this is it. We finish here. Thanks for your attention.